Let's take a look at an analog wave, which is typical of what is found in electrical signal and radio waves. A wave can be seen in terms of a 300-degree circle. We see in this particular example of a wave, this would be the 0-degree starting point, and a quarter through the circle or the cycle, we reach the 90-degree point. Then halfway through the circle or slash cycle, we reach the 180-degree point, and a complete circle or cycle is 360 degrees. So from starting point to the ending point, we complete the circle or the cycle. Okay, the height of the wave can be measured, and the height is known as amplitude. The length of the wave, or a complete cycle, from start to finish, is known as wavelength. Okay. The top graph represents an analog wave. And we see as signals, whether they are analog or digital, travel along a medium. That signal tends to break down or lose this original consistency, and we call that attenuation. And at some point, those signals will need to be regenerated, and we call that process amplification. Hence, you would need an amplifier to produce that effect. Okay, the bottom graph represents a digital signal. Digital signals are created when using pulses of as close to being as precise as possible voltages. And in this instance, we could assume that this amplitude is 1 volt, and 1 volt is maintained for a period of time, and then the power generator no longer sends power, and we see that we get an absence of voltage for a certain period of time, and then the generator produces power again for a certain amount of time. And again, as with the analog signal, as the digital signal travels the media, it too will break down and will require some type of repeater / amplifier. Okay. Well, at layer 1 of the OSI model, waves can be used by sending and receiving devices to send binary information. In this instance, amplitude modulation is used. We see that this bar represents 0 voltage, and perhaps this could be 1 volt. So we see that a 1 volt signal will be interpreted as a 0. A 2 volt signal will be interpreted as 1. And then we go back to the 1 volt signals. We see that they are again interpreted as zeros. And note the dotted lines that separate the cycles. We could basically refer to the areas in between the dotted lines as time frames or time slots. In this instance, we see one complete cycle per time slot. However, the difference comes in when the amplitude is manipulated. This could be electrical wave, or this could be a radio wave. Okay, now if it's a radio wave, then the power in this instance wouldn't be an electrical signal, but a radio signal, and it will be measured in terms of power and hertz. Right, we can also use the frequency to relay zeros and ones. In this instance, again, we see the 0 bar, and the dotted lines represent time frame. Okay. However, we see that in this particular example, an increase of a cycle changes the bit. So we have a relatively slow cycle, a longer waveform in this particular time frame. So therefore, the receiving device will interpret that particular signal as a 0. We shorten the waveform or increase the cycle. The receiving device will interpret the signal as a 1. Again, we slow the cycle, 0. Slow the cycle, 0. Maintain the slow cycle, 0, 0, 0. Increase the cycle. We get back to the 1 bit. Right? Zeros and ones can also be sent and interpreted based upon the phase of the wave. In this instance, we see that we start at 0 and we continue with the normal path of the wave, and the receiving device in this instance will interpret that path as a 0. But then if we shift directions or shift the phase, the receiving device will interpret the phase shift as a different bit, in this instance 1. Shift the phase again, back to 0, and we continue the cycle during each time slot, and we continue the 0 bit pattern. Shift the phase, and we're back to the 1 bit. Right, so let's take a look at the return to 0. Okay, in this particular graph, we see the time slots are demarked by a solid gray line. Okay. Again, we have the 0 bar. In this instance, represents 0 voltage. To produce a 1 bit, we start at the upper range of the time slot, but halfway through the time slot, the signal returns to 0, basically no voltage. And then to produce another 1 bit, we have to start the voltage, and positive voltage, that is, at the beginning of the next time slot, and halfway through that time slot, the voltage returns to 0 or no voltage. Again, we produce a 1. To produce a 0 bit at the beginning of the next time slot, we need to generate a negative 1 voltage. And halfway through that time slot, the signal returns to 0 or no voltage. To To produce a 1, again, we go with a positive voltage at the beginning of the time slot. But notice during each instance whether we're producing a positive voltage or a negative voltage at the beginning of the time slot, the voltage returns to 0 or no voltage. Okay? That's returned to 0. Non-return to 0 is different. To produce a 1 bit, we generate a positive voltage at the beginning of the time slot and maintain that voltage. Okay, and to produce a consecutive 1, then we maintain the voltage. To produce a 0, we go to a negative voltage and at the beginning of the time slot, and we maintain that negative voltage until it's time to produce another bit. In this instance, it's the 1, so we have to go to positive voltage. In this instance, we need to produce consecutive 1, so we maintain the positive voltage until it's time to produce a 0 bit. Then we go to negative voltage, maintain that negative voltage until it's time to produce positive voltage to generate a 1 bit. Okay. Okay. Non-return to 0 is just what it says. At no point does the signal take a pause at the 0 bar. Okay. There will be a positive voltage or negative voltage, but at no time a 0 voltage. Okay, at the physical layer, yes, we are concerned with how devices communicate in terms of actually generating and sending the signals and interpreting the signals, but those signals have to travel some type of media. This is an example of physical media that's used to connect devices and to use as conduits to relay those signals. Okay. We see there's a 10 base T standard, has a maximum transmission speed of 10, which is 10 megabits per second. Hence the 10 in base equals 10 megabits per second. Base is baseband, which is different than broadband, and the T indicates twisted pair cabling is required for this particular standard. And you can use Cat3 cable or above, and each segment has a maximum distance of 100 meters. And it's best to use a connectivity device such as a hub or switch to produce the star topology. Okay. All right, let's take a closer look at the 10 base T standard. It requires a 10 megahertz frequency, and it uses the Manchester encoding scheme. Okay. Let's take a look at the Manchester encoding scheme. Okay. All right, we see that there are 2 Manchester encoding schemes. We're going to focus on the IEEE 802.3, which is Ethernet, and we note that the time frames or time slots are be marked by light, solid gray lines. Okay, right? To produce a 1 bit, halfway through the time slot, we increase voltage, or we make a positive voltage. To produce a 1 bit, we hold that positive voltage until halfway through the next time slot. We go to negative